Okay, so we've modeled several situations, and you should try modeling different scenarios, different situations. I'll try to send you more examples, more questions at which you have to model. If you can't model, you can analyze the game. So modeling is the first and important step, okay? So, well, again, why did we model? We modeled in order to make predictions or prescriptions. The systematic way of making predictions or prescriptions we will call a solution concept. So a systematic way of making predictions for prescriptions for a class of games will be called a solution concept. So I'll denote script G. Question? Yes, sir. Okay. So I'll denote script G. I'll use script G to denote a class of games. Okay. So for now, script G will denote games that can be represented in strategic form games that in which agents behave, take an action as if they take their action simultaneously. So a solution concept, now I'm going to denote it with phi. What it does is it takes a game, let me denote it with, so I'll use capital gamma to denote a game, which consists of from now on I'm going to use the triple representation, a set of agents, a set of strategies for each agent, and a preference relation for each agent. It takes a game gamma and maps it to a subset of the strategy profiles of that game. Okay? So a solution concept takes a game and maps it to a set of strategy profiles. We will call this the phi solution concept, and this set we will call the phi solutions of gamma. Okay? So what we will do today is we will start studying different solution concepts. Okay? But before we get serious, let's play a game. So what I would like you to do is take one piece of sheet and pass it around. Write your name and ID number on the paper, please. Write your name and ID number on the paper. So the game that we're going to play is the following. It's going to be a two-person game. Okay. So what I'm going to do is I'm going to pick two students at random, okay, and look at the strategies that they picked. You have two actions, two strategies to choose from. I don't know, let's call them C and D. They don't stand for anything, just simple letters, C and D. I'll pick two students at random. And let's say that if they both have written C on their paper, I will not change their first homework grade. So the change in their first homework grade will be 0. But if one of them has written, so let's call the one on my left player 1, student 1, the one on my right hand, student 2. If student 1 has written C and student 2 has written D, I will increase the grade, let's say that, I will increase the grade of student who wrote C by 2 points. Well, let's be generous, 3 points. And decrease the grade of the student who wrote D by 10 points. And vice versa. Okay. If they both wrote D, I will increase their grades by 2. Let's say that's what we're going to do. Okay? So that's the game we're going to play. I will choose, so write either a C or a D. The game is symmetric, so it doesn't matter whether you're on my left hand or right hand. whether you're student 1 or student 2, I'll pick 2 students at random, and I'll do this for every pair, okay? If they both wrote C, their first homework grade will not change. Let's say that's going to happen. If one of them wrote C, the other one wrote D, the one who wrote C, his or her first homework grade will increase by 3 points, but the student who wrote D, his or her first homework grade will decrease by 10 points. If they both wrote D, I'll increase, let's say that, I'll increase both of their grades, first homework grades, by 2 points. Come on. Let's say that. 10 over 10, or okay. So you can destroy the whole first homework.
Can we collaborate or
well, who are you going to collaborate? Your pair is going to be some person random in the whole group. You can collaborate. I don't know. Think about it. Well, don't show it to anybody. So let's say that you're not allowed to collaborate. Okay? Actually, let me be even more generous. Let me make this 5. All this group, I'll count them later, has written C. And the rest, all this group, has written D. Okay? So let's think. So a majority has played C. So these, if they paired with one of the C people, they'll be having a tough time, at least when their first homework is graded. Well, let's say that that's the case. Okay. Now let's think. What should you have done, or why did people who wrote C or D write what they did? Anybody who wrote D, they volunteer to explain their reason why they wrote D? Do you have a question or comment? Anybody volunteer? Any volunteers who would describe why they wrote D? Anybody? Okay. Well, then let's think. So the problem here is you don't know what your opponent is going to play. Actually, in this case, you don't even know who your opponent is. It's some random person in this classroom. Okay? So let's say that you're player 1. Again, the game is symmetric. It doesn't matter who you are. It's just life is going to be a bit easier for us for illustrative purposes. Let's say that you're player 1. Okay? Now, it's a tough choice. You don't know what your opponent is going to play, so it's hard to choose what to play. But for a minute, let's think that somehow you learned or you strongly believe that your opponent is going to play C. Okay? What is your best choice? What would you do if somehow you learned that your opponent is going to play C? What would you do? Play C, right? If you had known that your opponent is going to play C, your best action is to play C. Unfortunately, you don't know. Okay. Well, maybe your opponent is going to play D. Well, let's say that somehow you learned that your opponent is going to play D. What would you do?
Depends on how nice you are.
Well, I'm assuming you prefer a higher grade to a lower grade. After all, you don't know who this other person is. Still.
You could be nice towards them
Without knowing who they are. Okay. So, I guess some of the people who played D was thinking that way. Okay. But again, if these reflect your preferences, if these numbers reflect your preferences, if you don't care about the second person, okay, if you don't know who that person is, or even if you know, you don't care about it. You only care about your own welfare, your own grade. Then what is the best thing to do? Again, to play C, okay? But we don't know if the opponent is going to play D. But you see what happened. If I had known that my opponent is going to play C, playing C is better than playing D. If I had known that my opponent is going to play D, playing C is better than playing D. But then, no matter what my opponent does, playing C is better than playing D. Okay. So, yes, sir.
So in general, the rational choice to play C?
Well, yes, so if people's preferences are represented by these numbers, that is, they prefer getting 5 to getting 2, okay, and they don't care about their opponent, the other student, then playing C would be the rational thing, okay? Again, the whole idea is, if I had known that my opponent is going to play C, playing C is better than D. If I had known that my opponent is going to play D, playing C is better than playing D. So no matter what I know about, even if I don't know what my opponent is going to play, playing C is better than playing D. So a rational person should play C. Okay? So again, those who play D probably these numbers did not represent their preferences. They were not only caring about their grade, but they were caring about the grade of the other unknown person. Okay? Okay, so far so good? So, it looks like a good prediction. So I would predict that anybody playing this game would play C. And looking at the numbers, there's always some room for error, especially when you're dealing with people. Okay, our prediction seems to be pretty good. Okay? Okay, so this will be, we'll formalize this. This will be our first solution concept. So first, let's give a name to this. We will say that the strategy of C of player 1 strictly dominates the strategy D of player 1 in this case. Okay? So let me give a formal description of that. Okay. So normally every definition I give should start with, let N Si let gamma be a strategic form game. From now on, I'm not going to write that, but every definition should start like this. Okay. So so let gamma be this game, and I a player of this game. Okay. The strategy Si prime of player I strictly dominates a strategy Si of player I if and only if the following holds. By the way, I'm going to email these definitions to you too, so you don't really have to write it. Okay. So, by the way, a piece of notation I have to introduce here. So I want to say, given here there was only one other player, so when I'm talking about player 1, there was only one other player, but in general there are many. So I need a notation to say, given the strategy profile of the other agents. So the notation that we're going to use is S minus, which stands for except I. So it's a list of strategies of players, of all the players, except player I. Okay? So this will be S1, S2, Si minus 1, Si plus 1, Sn. So that's the notation that we're going to use. A profile of strategies of all the agents except agent I. Okay? So given a profile of strategies of all the agents except agent I can play Si prime or Si. Okay. So what we want is, just like here, if player I had known what his opponents are going to play, playing SI prime should always be better than SI. So, and we want this to hold for every strategy profile of the other agents. Okay? So far, so good? We could have written this using numeric representations, just as saying UI SI prime S minus I is greater than UI SI S minus I. Okay? So far, so good? So here, C strictly dominates D. The strategy C of player 1 strictly dominates the strategy D of player 1. And actually, the same is true for player 2. If player 2 had known that player 1 is going to play C, playing C is better than playing D, if these numbers represent his preferences. If player 2 had known player 1 is going to play D, playing C is better than playing D. 5 is bigger than 2, so playing C, given that his opponent is playing D, is better than playing D, given that his opponent is playing D. Okay? So far, so good? So, by the way, just a word of warning. Some books, some papers, some game theorists call this domination. So they define it as SI prime dominates SI if this condition holds. Okay? Some call this strict domination, some call it domination. Okay? This is what we're going to use. If you're using Osborne's book, this is what Osborne also uses. But if you're using some other book, don't get confused. Some game theorists use a slightly different notation. They call this domination, okay? And we're going to define a weaker notion than this. They call that weak domination. I would call that domination, okay? So a strategy SI prime of player I is strictly dominant strategy of player of agent I if and only if SI prime strictly dominates any other strategy of player I. Okay? So here, strategy C of player 1 is a strictly dominant strategy because, well, player 1 only has one other strategy, which is D, and C strictly dominates D. So C is a strictly dominant strategy of player 1. The same is true for player 2. Okay? So we will use D star of gamma to denote the set of strictly dominant strategies of player I in the game gamma. Okay? So in the prisoner's dilemma game, D star gamma PD, I will use this notation to denote the prisoner's dilemma game, just consists of C. Okay. Similarly, D star 2 of gamma PD is also equal to C. Okay? Sure. How can we have, so we're checking. Uh-huh.
So how can we have two sigma-dominant strategies?
Okay, good question. So how can we have more than one strictly dominant strategies? Okay, so actually, I'm glad that you brought that up. So Actually, let me give one more definition, and then we'll come to that. Okay. So I will use d star of gamma to denote the Cartesian product of di star of gamma over the set of all agents. So this will be called the set of strictly dominant strategy profiles of gamma. It will also be called the strict dominant strategy solution. So this will also called d star will be called the strict dominant strategy solution concept, and d star of gamma will be called the strict dominant strategy solutions of gamma. Okay? So once you have a new animal in your world, there are certain questions that you have to ask. One of the first questions you should ask is, does it always exist? Does every game have a strictly dominant strategy solution? Okay, sorry? No. So if you claim that it's not the case, you have to give us a counterexample. You have to give us an example. Any?
A game where no strategy exists, like a chance game.
Well, let's leave chance games out of our world for now, but we'll get to that. Let's think simple.
If 2 is greater, yeah, 6.
If this was 6, for example, okay, so does C strictly dominate D? Well, when the opponent plays C, C is better than D. But when the opponent plays D, D is better than C. So C does not strictly dominate D. And now I have to check, maybe D strictly dominates C. That's not the case either, because if the opponent plays C, playing C is better than playing D. So in this game, if we change that 2 to 1, D1 of gamma is empty. D1 star of gamma is empty. Hence, D star of gamma is also empty. Okay? So, it doesn't always exist. Unfortunately, actually, for most games, the set of strictly dominant strategy profiles is empty, which is a problem for us because it means that you won't be able to make any predictions, you won't be able to make any prescriptions. That's bad news. That's some unfortunate thing about strict dominant strategy solution concept. The next question you should ask is the question that your friend asked. Well, when it exists, how many can there be? Is it always unique? Can there be infinitely many? So in a game, at most how many strictly dominant strategy solutions can we have? The number of strategies. Everybody agree? Yes, sir?
It's not that I missed that part. Why is that set empty? The second set.
The second. Okay, well, okay.
C dominates equal 13.
Okay, so for player 2, D star of gamma is C. So what was D star of gamma? It's the Cartesian product of these two sets. The Cartesian product of the empty set with the sets which contains C, D star gamma is empty set Cartesian product C, which is empty set. It's empty because of this. Okay? Okay? But thanks for bringing that up. Okay. So let's go back to the question. At most, how many strictly dominant strategy profiles can a game have? By the way, this question actually boils down to, at most, how many strictly dominant strategies can a player have? Okay? Because you're taking the Cartesian product, the number of elements in this set will depend on the number of elements in these individual sets. So that's a simpler question. In any game, at most, how many strictly dominant strategies can a player have? Yes, sir. As the number of players, anybody else? Number of strategies minus 1. Anybody else? Anybody else? Only 1? Anybody else? Only 1? Okay, so why only 1? Because it's strictly. So dominant. You see, the condition we're looking for is this. If you're using numeric representation, it's this. If you're using preferences directly, you're using this. So let's say that. Let's do it by contradiction. Let's assume that there is more than 1. Okay? Assume that the cardinality of di star of gamma is greater than 1 for some player. Okay? Then it means that it has at least 2 elements. Okay? So let Si prime, Si double prime both be elements in di star of gamma. Okay? Here, Si prime is different than Si double prime. I know that 2 such elements exist because there's more than 1 element. Okay? So Si prime being a strictly dominant strategy means that this condition, by the way, which one do you prefer? Numeric representations or preferences? Numeric representations, so economists are usually used to working with, well, they call it utility functions, but numeric representations, so let's do it. So since Si prime is a strictly dominant strategy of player on, what do we have? We have, for any strategy profile of the opponents, Ui Si prime S minus I is greater than Ui of Si S minus I. For which Si? Okay, so what was the condition for being a strictly dominant strategy? The condition was it should strictly dominate any other strategy of player I. Okay, so this holds for every Si strategy of player I different than Si prime. Okay? But then Si double prime is a strategy of player I different than Si. What does that imply? Ui of Si prime S minus I is for any S minus I is greater than Ui of Si double prime S minus I. Since the statement is true for any other strategy of player I different than Si prime, it's also true for Si double prime. So that's what we have. But if this is the case, can Si double prime strictly dominate Si? No. Okay. Strictly dominate Si prime. Contradicting the fact that Si double prime is a strictly dominant strategy solution. Okay? So we have arrived to a contradiction. Hence, how do we arrive to that contradiction? By assuming that this is the case. So it means that in any game, any player can have, if this is false, what is true? This is true. In any game, any player can have at most one strictly dominant strategy. Well, if each of these sets contains a single element, the Cartesian product will also contain a single element. So any game can have at most one strictly dominant strategy solution. Okay? Which is good news, because it says that when you're making predictions, you can make exact predictions. When you're making prescriptions, you make exact prescriptions if you use this method to make predictions or prescriptions. Okay? The bad side is, most of the time, it's empty. The good thing is, well, when it's not empty, it contains only one element. So it exactly lets you pinpoint what they would or should do. But for most games, it says nothing. That's bad. And that's really, really bad because for a large class of games, that's the case. Okay? There's one other thing which is good about this solution concept is, you see, when you're checking whether a strategy profile is a strategy is a strictly dominant strategy of a player, all that you're using is the preference of that agent. So when agent I is trying to decide whether he has a strictly dominant strategy or not, all he needs to know is his own preferences. He doesn't have to know anything about the other players. This is also something good. Informationally, it's very minimalistic. Okay? So it has two good points. Agents only have to know their own preferences to find strictly dominant strategies. Okay? And when a strictly dominant strategy solution exists, it's unique. That's also good. The bad thing is, most of the time, it's empty. It doesn't exist. So what we have to do is maybe relax this condition a bit. Maybe this is too strong. Okay? So one way to relax this is get rid of the strict parts and state the following: if and only if, okay, for any strategy profile of the opponents, so I'll use numeric representation, playing Si prime, given that the opponents are playing S minus I, is at least as good as playing Si, again, given that the opponents are playing S minus I, okay? And for at least one strategy profile of the opponents, playing Si prime is strictly preferred to playing Si, given that the opponents are playing S minus I. Okay? So in this case, we will say that Si prime dominates Si. Okay? And then, so all we're doing is relaxing the condition, and then we say that a strategy Si prime is a dominant strategy of player I if and only if Si prime dominates any other strategy of player I. We'll remove the star from here. So that will be the set of dominant strategies of player I. And then the rest goes on as the same. So raise the star, raise the star. Okay, so far so good? So far so good? So now we have a new animal. So this is our second solution concept, the second method that we can use to make predictions or prescriptions. Okay. Again, whenever you have a new animal, the first question you should ask is, does it always exist? And the answer is? And the answer is? No, right? The example that we just had actually is an example for that. It's that your friend had suggested. 0, 0, what was it? 2 minus 10, minus 10, 2, and 6. I forgot what we had here. 3, well, it doesn't matter, okay? Here, player 1 does not have a dominant strategy, okay? So, again, actually the problem here, well, but for example, if this was the case, then what can we say about D1 of gamma? Actually, what can we say about D1 star of gamma? It's it's empty. Player 1 does not have a strictly dominant strategy because if he knows that his opponent is playing C is strictly better than playing D. But if he knows that his opponent is playing D, C and D are equally good. So C does not strictly dominate D. Hence, player 1 does not have a strictly dominant strategy. But he does have a dominant strategy, right? C is better than D if he knows that his opponent is going to play D. C is not worse than D when he knows that his opponent is going to play D. So for every strategy of his opponents, C is at least as good as D. And for at least one strategy of his opponent, that is in this case, when the opponent plays C, playing C is better than playing D. Playing C is better than playing D. So C is a dominant strategy of player 1. So the strict dominant strategy solution concept does not make any predictions for this game, but the dominant strategy solution concept does. But again, unfortunately, for most games, it doesn't make any predictions at all. It's empty valued. But again, it has the nice thing. When it exists, we can do the same things here. When it exists, there is at most one dominant strategy. Okay? Okay. So when it makes a prediction, it makes a unique prediction, which is good. Okay? Again, when we look at it, it only uses information about player I's preferences. That's also good. Now this is our second object. So a new animal has entered our world. The next question you should ask yourself is, how are these animals related? How is strictly dominant strategies and dominant strategies related? What is the relation? Is there any? Yep. Strictly dominant strategies are, so D1 star of the I star of gamma is a subset of di of gamma. Actually, can we even say more than this? First of all, most of the time this is empty. If it's empty, the statement holds trivially. Well, when it's not empty, what happens? They're equal. So actually what we can say is, whenever a player has a strictly dominant strategy, then the set of dominant strategies of player I is equal to the set of strictly dominant strategies of player I. Bless you. Which is also something good. You see, this was the first solution concept we came up with. It's a very reasonable solution concept. The reason that we looked for something new is because it's most of the time empty valued. It doesn't make any predictions. So what this says is that, well, if you use the solution concept, whenever a strictly dominant strategy exists, that will also be a dominant strategy. Okay? Well, when it doesn't exist, then, this may or may not exist. So which is something good. In a way, it preserves what we already had. Okay? So far, so good? Any questions? Any questions? Yes, sir.
Can I look at the definition?
Sure. Actually, let me write it better. So no matter what your opponent does, SI prime should not be worse than playing SI, given that your opponents are playing S minus I. And for at least one strategy profile of your opponents, playing SI prime should be better than playing SI. Okay? Any questions? Any questions? None? Okay. Well, before we go, before we take a break, let me go back to the game that we just had. I think I wrote something 5. I forgot what the numbers were. Sorry about that. By the way, does this game ring a bell? Is it familiar? It's exactly the prisoner's dilemma game. All we did is just use the different numerical representation. Okay? But it's the prisoner's dilemma game. The preferences are the same. For player 1, CC is preferred to DC. Okay? CC is preferred to CD, which is preferred to DC, and so on. This is exactly the prisoner's dilemma game. All we did is use a different numerical representation. Okay? So our prediction for the prisoner's dilemma game is that both players would play CC. Okay? Okay? So where does the name prisoner's dilemma came from? Well, we know where the word prisoner comes from. It's about 2 prisoners. Why the dilemma? Why not just call it the prisoner's game? Okay, so 2-2 is, so those who took 204 know about Pareto efficiency, Pareto optimality. But does everybody know about Pareto efficiency? Pareto, not everybody, so we'll have to give it. So the thing is, when you look at it, playing DD, both players prefer the outcome that results from playing DD to the outcome obtained by playing CC. So DD, in a way, is socially better than CC. When we move from CC, both players become better off. Okay? Such a situation, we say, in such a case, we say that DD, Pareto dominates CC. Okay? Let me give the definition and we'll take a break. A strategy profile S prime, so that's a profile, not a strategy. Pareto dominates a profile S if and only if for every player, the strategy profile S prime is at least as good as the strategy profile S. That is, the outcome induced by the strategy profile S prime is at least as good as the outcome induced by the strategy profile S. And there is at least one player for which the outcome induced by the strategy profile S is preferred to the outcome induced by S. Okay? So if these 2 conditions hold, we say that S prime Pareto dominates S. We will say that S prime in S, again, profile, is Pareto efficient if and only if it is not Pareto dominated by any other strategy profile. Okay? Be careful. So Pareto efficiency doesn't mean that Pareto dominates everything else. Okay? So S prime Pareto efficient doesn't mean that Pareto dominates everything else. It means that it is not Pareto dominated by any other strategy profile. Okay? Students usually get confused here. Okay, when they see Pareto efficiency, just like when you see optimization, you know, if you say something is maximal, it means that the function takes a larger value than any other point. So when they read this Pareto efficient, they think that Pareto dominates everything else. That's not what it says. It says that it is not Pareto dominated. Okay? So let's take a 10-minute break. After the break, we'll try to understand what this says.